For years, SAE Level 2 autonomous systems have relied on a straightforward safety protocol known as fail-safe. When the system detects an internal fault, it shuts down steering assist and relies on an immediate mechanical fallback, the human driver. SAE Level 3 autonomy breaks this model. At this level, the driver is legally and physically disengaged from the control loop. They are not required to watch the road, which makes them unavailable for immediate emergency corrections. Because the driver cannot intervene, the ISO26262 standard mandates the highest automotive safety integrity level, ASIL-D, for Level 3 steering architectures. The math is absolute. A single point fault in the hardware cannot lead to a loss of lateral vehicle control. Meeting the standard requires a transition from fail-safe to fail-operational design. To maintain control entirely on its own, the system must deploy total, physically isolated redundancy across its power supplies, communication networks, microcontrollers, and motor windings. A Level 3 steering system has to survive the catastrophic death of its own primary hardware, diagnose the failure, and transfer control to a backup circuit without the vehicle ever leaving its lane. The engineering parameter dictating how quickly the system must save itself is called the fault-tolerant time interval, or FTTI. The FTTI represents the hard physical limit of the vehicle's trajectory. If a car is traveling 50 kilometers per hour on an 88-meter radius highway curve and loses steering assist, physics dictates that the vehicle's outer tire will cross the white lane line in exactly 740 milliseconds. However, engineers cannot use that entire duration. Factoring in mechanical latencies and mandatory safety margins, the functional system budget to resolve a critical failure is compressed to a strict 240 milliseconds. To see exactly how a modern steering controller beats that clock, we are going to track a worst-case scenario, a total short circuit inside the primary inverter, and break down the 80-millisecond handover sequence required to keep the car on the road. Surviving this fault at highway speeds requires the redundant hardware to execute a deterministic, hyper-synchronized series of logical handshakes measured in fractions of a second. This horizontal timeline maps out our fault constraints. The sequence begins at 0 and stretches to the physical lane departure limit at 740 milliseconds, with our total functional budget capped at 240 milliseconds. At precisely 0 milliseconds, a single point fault occurs, a high-side MOSFET short circuit inside the primary inverter. The main hardware is dead. Over the first 20 milliseconds, that physical short generates a massive current overshoot. The analog-to-digital converter channels in the primary microcontroller unit, or MCU, instantly capture this erratic spike. To verify the data, the MCU relies on internal parallel lockstep cores. These twin processors execute identical calculations simultaneously. When their outputs diverge because of the current spike, the hardware registers a real-time anomaly. Between 20 and 30 milliseconds, the system runs through a debouncing phase. Logic gates process the anomaly to filter out any transient electrical noise, confirming that the voltage spike is a hard physical fault and not a temporary glitch. By the 30-millisecond mark, the primary controller has mathematically proven its own hardware is fatally compromised. The schematic details the dual MCU architecture that takes action next. Between 30 and 35 milliseconds, the system initiates the inhibition phase to satisfy technical safety requirement 01, the prevention of unintended torque. The primary controller executes a fail-silent protocol. It immediately halts all pulse width modulation signals and physically cuts power to its gate drivers, completely severing itself from the motor. At the exact same time, moving into the 35 to 40 millisecond window, the dying primary controller must transfer command to the secondary backup. It transmits a critical handover flag across a highly secure, redundant SPI or PCIe heartbeat link, signaling the secondary MCU that the primary is offline. Aggressively shutting down the primary hardware is the only way to prevent the damaged inverter from injecting catastrophic, asymmetrical torque directly into the steering column. This data flow graph shows the internal state of the secondary MCU as it enters the arbitration phase at 40 milliseconds. Upon receiving the handover flag, the backup unit runs a rapid self-diagnostic to confirm its own health and then officially promotes itself to master control. If this backup unit were running as a cold standby, meaning if only booted up after the fault occurred, it would take precious milliseconds to calculate the steering trajectory from scratch, resulting in a fatal torque jump. Instead, Level 3 systems utilize a hot standby architecture. Before the fault ever happened, the primary controller was already mirroring critical telemetry, including the integral target, current steering angle, and active motor current, to the secondary unit via 100 Hz CRC links. As the timeline hits 60 milliseconds, the secondary unit moves into the initial torque calculation phase. Because its memory buffer is already fully populated with the exact trajectory data, it can calculate the optimal transition torque instantly, without starting its logic loops from zero. Continuous memory mirroring allows the backup controller to pick up the steering algorithm exactly where the dead hardware left off, preventing any violent mechanical disruption. This diagram shows the specific actuator that applies the lateral force, a dual-stator permanent magnet synchronous motor. Inside this single motor are two separate, physically isolated sets of three-phase windings. Between 60 and 80 milliseconds, the secondary inverter activates, driving calculated power exclusively into those independent secondary windings, while the primary side remains completely dead. Here, the system must adhere to Technical Safety Requirement 03, which strictly limits how fast the backup torque can be applied to the steering rack. The software enforces a strict torque slew rate limit for the first 50 milliseconds of actuation. Instead of dumping power into the motor instantly, the current climbs smoothly along a controlled curve to prevent mechanical shock. This engineered ramp-up seamlessly restores over 80% of the required assist torque without jarring the physical steering mechanism. At 80 milliseconds, the handover sequence finishes. The broken hardware is isolated, the backup unit is active, and lateral control is fully restored. Looking at the complete 0 to 740 millisecond timeline, we compare the 80 millisecond completion point against the 240 millisecond functional budget and final 740 millisecond physical boundary. Completing the hardware transition here secures an architectural victory, a massive 160 millisecond safety margin. This margin is not wasted space. It gives the secondary controller time to dampen out residual vehicle oscillation caused by the initial torque loss. The lateral dynamics of the car are completely restabilized hundreds of milliseconds before the vehicle ever approaches the white lane line. A successful ASIL-D architecture executes its corrections so deeply within the physical margin of error that the human occupants never even feel the hardware fail. Fail operational design depends on total system isolation rather than simple hardware duplication. Vehicle survival is reliant on continuous data mirroring, aggressive electrical isolation of completely damaged components, and tightly controlled torque limits to manage the physics of the handover. ISO26262 demands these sub-100 millisecond hardware transitions to be mathematically deterministic, designed so that every single microsecond is accounted for and actively managed. As the industry scales Level 3 autonomy to higher speeds and complex highway environments, mastering this temporal choreography is the baseline standard for consumer trust. Hardware will always fail. Guaranteeing mathematical redundancy within the exact bounds of physics is the primary engineering requirement for finally allowing a human driver to safely let go of the wheel.